Okay, can you hear me now better? Okay, so my talk would like basically to introduce those kind of multivariate permutation tests. We are dealing with those methodologies since a long time, also with my my colleague Fortunato Pesarins and our group in Padova, and this is a joint work with Rosa Arboretti and Riccardo Ceccato. So the aim of the talk is basically to try to introduce to all of you this technique and showing you some applications along with some simulation results, how it behaves also compared with a few others that we found in the literature. So the focus is multivariate, goodness of fit, and stochastic ordering permutation testing. First of all, let me start in giving a quick overview of how it was increasing the research over the years related to permutation tests. So this is just a quick shot from Scopus, and you see that there is an increasing trend. So in the last 20 years, there are over 3,500 publications connected with permutation tests, and some of those are dealing with multivariate permutation tests. The main reason is that those kind of methods are quite flexible in dealing with the dependency among the several variables. And recently, this methodology that I'm going to introduce you has been also implemented in a quite well-known software within the area of non-parametrics and permutation tests and exact inference, which is StatExact. And also, we have a collaboration with some colleagues from Berkeley to implement also a repository in Python. So for those of you that you might be interested in also the computing part, there are plenty of repositories with R codes, Python codes, and also a standalone software like this StatExact 12. So this is the overview of the presentation, and of course the problem is the one you all know very well. So goodness of fit problems can be introduced like that, and if you go with two samples, then you can also use two sample tests to approach a goodness of fit testing problem, assuming that you are drawing the observation from the reference sample, and you consider this reference sample as a second sample. So basically, what I'm going to show you is how to deal with testing for the equality of two distributions for any type of variable, so they can be continuous, ordinal, and also we can easily extend the univariate situation to multivariate situations. The general scheme for multivariate setting is the one you see here, where basically you use a sort of union intersection tests to build up the system of hypotheses when you are in the multivariate situation. So suppose you are observing capital V variables, and you want to test the equality of the distribution functions on those V-dimensional multivariate setting against the difference in distribution. We will see later that we can easily apply this system, this procedure to directional alternatives, and also to for testing for a trend, so testing for a stochastic ordering. The basic tool is the non-parametric combination methodology. So a few steps, a few quick hints on how to apply this methodology to derive a univariate test and then to go with the multivariate one. First step is to find out a suitable test statistic for the problem at hand. Of course, here you have several choices because, as you might know, permutation tests are quite flexible in this. One choice that I will be using also later for the simulation study is to consider the well-known Anderson-Darling statistic. But of course, this could be Kolmogorov-Smirnov type statistics or a Kramer von Mises or whatever type of statistics. So, of course, this is the choice of the test statistic is very much related to the power that you can get from the univariate procedure. Then, first phase is to start building up a permutation test for each variable that you are considering in your problem. So you are basically building marginal tests, one for each variable that you have in your multivariate problem. The procedure is the usual one for building up a permutation test. So basically, you start by applying the test statistic to the vector of observed variables, so assume that you have more than one variable, and for each one you apply the test statistic. Then you start shuffling the data between the two samples, or the more than two samples if you are in a stochastic ordering situation, for example. But we will see later this. So you start shuffling the observations, and then you apply the test statistics at any shuffling of the observation. Then the key part is to find out how the observed value is located in the permutation distribution, and this gives you the p-value for each of the variables and for each of the single test statistics, the univariate one that you considered. So far everything is standard. The key point is what happens when you are in a multivariate setting. So in a multivariate setting, basically you have more than one variable. So here is the situation that I was referring also at the beginning. So you have capital V variables. And the trick here is to permute the entire vector of the observation. So you are taking the rows of your data set, basically, and you are shuffling the entire row of your data set with another one in the other sample. This allows you to produce a permutation distribution, a multivariate permutation distribution of your data, without the need to take into account about the dependency among the test statistics, because you are just shuffling the rows of your data set. So you do not need to know which is the dependency. You simply are taking into account indirectly of the dependency that you have in your data. Then, for each of the variables, here you apply a permutation test. So basically you come up with a representation like that, where you have the observed value of the permutation test without shuffling, and the permutation distribution of all your values, the permuted values for each variable. You have V variables, capital V variables, so you have basically a multivariate permutation distribution of the test statistics. Now, how to come up with a multivariate test from this setting? The point is find a suitable function that can combine all the data. So we found out that if you can select a combination function that maps from the interval 0, 1, V-dimensional interval, capital V-dimensional interval 0, 1 to R1, that has these properties, so it is basically non-increasing in each argument, attains the supremum value even when only one argument, that in our case are the marginal p-values, goes to 0, and for every alpha that is fixed a priori, the critical value is finite and strictly smaller than the supremum. So any function that satisfies those three very basic properties can be one function to consider. Why this? Because it is proven in a couple of theorems that we have in some papers that this provides you a combined test that is unbiased and consistent. So these are two basic properties in testing procedures that you should have. And if the functions satisfy those three properties, you finally get a test that is unbiased and consistent. So three examples of those combining functions are like those three. So this is the well-known Fisher omnibus combining function, which basically is the summation of the logarithms of the p-values. The tippet one, the liptag. So the tippet is also is also called the complement the same as considering the maximum of the test statistics, and the Liptak one. So of course the choice of the combining function provides you different power for the testing procedure, and it can be suitable to different situations. So for example, if you have you expect many variables to be under the alternative, then some like Liptak can provide you quite good power. If you expect a few, then maybe Tippett has a good power, etc. So we found out later when several people from medicine, from industry, from engineering started to apply this system, this non-parametric combination, we found out that you can come up with, of course, quite different results at the end according to the combining function. Because what affects the combining function? The dependency, the choice of the test statistic, and of course the data you have. The point is which is a suitable combining function. So should I go all the time with Fisher, because more or less from several studies, there are some papers also, not only from our group but other groups, is the one that provides quite good power in several situations. Should I go with Tippett because it picks up the most important variables? So here there is a debate, so it is an open discussion, mostly because for the choice of the combining function, the thing is that you should choose some combining function that guarantees at least to have a good power. And we were working on this problem and found out that there is one function that is not reported here called iterative combining function that basically iterate the combination using different combining functions and come up with a quite stable result. So we proposed this for a couple of problems, and we published a paper in Statistical Methods for Medical Research with a couple of applied problems, and it looks like this could be a good choice from the practical perspective. The other point is how the dependency influences the combining function. And this is something that, of course, you do not need to understand when you apply this system, because, as I told you at the beginning, the dependency is already taken into account without the need to estimate it. But we had a question from practitioners to give some hints about which could be the dependency structure of the data. So, and we are still working with this problem, and this is something that I give you also as an open point. Now, let me complete how we can apply those combining functions in order to come up with the multivariate p-value. So, in order to come up with the p-value related to the comparison of the two multivariate distributions. So, basically, we apply the combining function. So, we come back to this. We come back to this stage here, and we start taking the vector of the p-values for each permutation and for the observed one, and we apply the combining function to all those vectors. So basically, the algorithm is like that. So applying the combining function to the vectors of p-values, or equivalently of the test statistics, that we found out in the previous step when we created the permutation distribution. And then we are going to create the permutation distribution of the combining function. So you see the structure is like that. You start with this permutation distribution of the test statistics. You can transform easily the test statistics into p-values, and then you start applying to the vectors, the v-dimensional vectors of p-values, you start applying the combining function. And you got the distribution, permutation distribution of the combining function, which is this one here below. Then from this permutation distribution, you can locate how extreme is the observed p-value. the observed test statistic, and then you can calculate easily a p-value from this permutation distribution. So basically, this is the procedure. Now, we try to apply this procedure to two-sample multivariate goodness of fit testing problems, and we wanted also to find out some competitor to compare our procedure with some other. Here we had some difficulties, so I also asked Simos to help us in finding some competitors. It was not so easy. So basically, if you have some hints, some suggestion of what we can also use, I would be really very happy to know. We found this possibility, this paper by Leckley and Rizzo, that they call this test an energy distance test. Probably you might have heard about that. Basically, this test is a test which estimates the limited distribution starting from this test statistic using a bootstrap sampling from the mixture of the distributions of the two samples. And there's another contribution from the literature, this paper by Baringhaus and Franz in 2004, which uses a similar test statistic. So this is quite similar test statistic, but in order to estimate the distribution, they use kernel functions, and particularly this kind of kernel function. And again, they use Monte Carlo bootstrap methods to estimate the distribution of the test statistic. As you see, those two tests are based on distances, so basically they are suitable for continuous variables. One feature of the multivariate permutation test is that you do not need to have only continuous variables. You can apply this test to continuous variables, to ordinal variables, or also you can have in the same problem mixed variables, so some continuous and some that are ordinal or even nominal variables. For our simulation study, that I would like to present only a few of the simulations, we considered different cases, like some all continuous variables, ordinal variables, mixed variables, and differences in location parameter, scale parameter, or also differences in both location and scale parameters. For generating, so we basically consider these three distributions, but the situation is similar also if you consider other distributions, maybe some skewed distributions, or even further heavy tail distributions. For ordinal variables, we consider this quite interesting algorithm by Barbiero and Ferrari to generate correlated ordinal variables. This GenOrd is quite efficient. And you see here we consider 6 components and a correlation that was kept constant at 0.25, but of course this can change. So I will go quickly through some simulation results, because I would like also to talk a little bit, maybe 1 minute, about the stochastic ordering procedures that we can solve also using this methodology. So here you have what happens in the power of the test when you, out of the 6, you have an increasing number of variables that are under the alternative. So you see basically the green line is under the null hypothesis, all variables under the null hypothesis, and then we start picking up some of those that are under the alternative. So 2 of those, 4 of those, or 6 of those. And you see how power, how is the situation with respect to power. Basically this is the area with most interesting one, so close to low values of low alpha values. Here you have the situation for the different distributions when you modify the location parameter. Here you have the comparison with the competitors that I mentioned before. You see that one of those, this is called Kramer, is a little bit conservative under the null hypothesis. Instead, in power, we have this behavior, so they are not so far, all 3. Slightly better the permutation one. This is the situation when you change the scale parameter, and this is the situation when you change also scale and location and scale parameters jointly. This is again the situation with the competitor. So you see when you change location and scale parameter, they are really very close each other in the interesting part of the distribution of the alpha values. Now, let me jump to, because I see the time is running, so let me jump to the stochastic dominance problem. So same methodology that I just presented can be applied for stochastic dominance problems. So basically when you want to assess a direction in the alternative hypothesis, for the multivariate problem that you are dealing with. Of course, here you have to change the test statistics. So this is the new test statistics that we are considering for each variable. And then the procedure is exactly the same. So you start permuting and combining the test according to a suitable combination function. Another situation that can be of interest is the situation of stochastic ordering. So if you have more than 2 samples, so assume you have C samples, and you think there is a trend among the samples, so maybe they can be increasing levels of a treatment according to different dosages, and there might be also an increase so you want to test if there is an increase along the treatments for the several variables that you have in your problem. This can be also solved using the same system, the same procedure that I showed you before. The only tricky part, I will show you here, is the way you permute. So basically, in order to solve these stochastic ordering problems, we are going to permute the data by pooling the data sets from time to time like this. So here you have a situation, for example, with 5 different samples that can be stochastically ordered, so they are multivariate samples stochastically ordered, and you basically start permuting by comparing the first sample against the other, the first 2 against the other 3, the first 3 against the other 2, etc. And you gain some p-values from those comparisons that you're going to combine. We have a couple of papers if you are interested, so now there is not so much time to go into the details, but this procedure turns to be quite effective. So if you are interested, there is a paper in biometrics about the application of this procedure for ordinal variable. Okay, so let me give you an example at least of this case. So here we have, for stochastic ordering, we have 4 groups of mice that were affected by a tumor, and they were treated with increasing doses of a drug. So basically we expect that as much as the dosage of the drug increases, as much as the volume of the tumor masses along times, so this is a repeated measures problems, reduces. So basically the testing of hypothesis is like that. So you have the equality in distribution of the four samples under the null, and a stochastically ordered alternative hypothesis like that. So the first dosage, which is the lowest one, has the highest volumes for the tumor masses, and the highest dose has the lowest volume for the tumor masses. So basically the data are like that. So here you have the treatment and the volumes, and you can easily apply this permutation procedure along times, so that to have also a partial test for each of the times. So we have 17 times, so 17 time occasions where those mice were observed. You can have a p-value for each of those times and a global one. So the result that you see here is a global one that states that globally, overall, for all times, there is a stochastically ordering of the treatments. So to conclude, this procedure is quite effective for different problems, so can be adapted for goodness of fit problems, stochastic dominance problems, so dominance of from one variable with respect to another, stochastic ordering problems, and it has an interesting feature which is called finite sample consistencies. And now, to give you a more up-to-date word, we should talk about thick data. So we have big data, large sample sizes, and we can have thick data when you have small sample sizes but large number of variables. So when you are in this situation, like in genetics, where you have few data but a large number of variables, you start applying this procedure, you can gain power by having several variables in your problem, independently of the sample size. So this is proved to be a finite sample situation that could be quite interesting and to be investigated more. So to give you a hint of how this works, here you have an increasing number of variables. So here you start with 2 variables, 6 variables, 10 variables, 20 variables. Assume that all variables provides non-centrality, so they discriminate between the 2 samples, or they provide differences in stochastic ordering problems. And you see the power of the multivariate procedure is monotonically increasing. So as much as you add variables that can be informative, of course, not random noise, but informative, as much as you gain power from this procedure. So this could be something also interesting to know about the procedure. Okay, so I think I can stop, and thank you very much for your attention. Thank you.
I don't need it, but thanks. I just wanted to ask you, your results where you show that your combination method is valid under the null and the alternative, are they only for permutations or any kind of resampling?
No. Okay. So we are strictly referred to conditional resamplings, so to permutation tests, not bootstrap tests. Of course, this procedure can be also extended for bootstrap situations, but basically what I was referring to is strictly within permutation tests.
And just a comment, you were asking for competitors. I guess that there are many. All the tests that compare for the 2-sample problem in the multivariate case. You have papers by Bickel from '69, where he uses permutation that he compares empirical distribution functions. You have the same thing done then by Prestgard and Wellner and all these guys using permutation, bootstraps, etc. So I guess these are your competitors.
So, thank you for the suggestions. I will take a note about that. Basically, the thing was to find some procedure that was comparing can be suitable for mixed variables. Okay, very good. That is good. Okay, very good. Thank you.
Any more questions?
Okay.
Okay, we can thank the speaker.
Hi. Okay. Yes, please. All right. Right. So thank you very much for the introduction. So, well, first I would like to start by thanking the scientific committee for the invitation. It's really nice to be here. Also, I would like to thank the organizers because so far the meeting has been perfectly organized, and that's really great. So, I'm going to talk about this joint work with Paula Navarro Esteban and Juan Antonio Cuesta Albertos, both from the University of Cantabria. And basically, the outline of the talk is the following. I would like to start with providing some context on why testing for uniformity with hyperspherical data, and give a brief overview of several uniformity tests that afterwards I will need that for referring to connect my proposal or our proposal to this uniformity test, and then provide some relation with a very well-known class of uniformity tests, which is the Sobolev class. And then hopefully, I'm not getting this correctly, okay. Hopefully, if time allows, I will have some time for simulations. All right, very well. So then let's go with the context. So why testing for data, why considering data in the hypersphere, right? So basically this kind of data arises the moment that you are interested in directions and not in the magnitudes. When you're dealing with multivariate data, several domains of application, for example, in astronomy, in biology, there are few applications. And basically the statistical challenges relate to the non-Euclidean support and the fact that there is no canonical order, and just a very unbiased selection of books devoted to the topic from people in this audience. These three ones, which show some that there is an activity on the field. All right. So why testing then for uniformity in the hypersphere? Well, perhaps this is the most fundamental question. If you have IAED data on the hypersphere, well, if it is uniform, then there is nothing else to do. And beyond that, it's an interesting auxiliary tool for other problems. For example, if you want to test for spherically symmetric distributions on RP, or for proposing goodness of fit tests on the circle, as well as for testing rotational symmetry on a sphere that is of a higher dimension, right? So that can be related with testing for uniformity in a lower dimensional sphere. So these are heavily addressed topics so far. From 1999, more than 30 non-parametric tests, so excluding all the parametric tests, and then hopefully by the end of the talk, 3 more. All right. So let me give a brief overview of uniformity tests. So, well, this is really simple goodness of fit setting problem. I mean, the distribution is completely specified. Well, there is nothing to estimate. The only perhaps tricky part is that you have to respect the rotation invariance of the null hypothesis. So any test of statistics should be rotation invariant. And then there have appeared several tests, mainly for the circle, that can be grouped into five main categories, based on the empirical cumulative distribution function, the Watson test. I will briefly review that, and then other based on partitions on the circle, and then you compare what is the expected number of points against what they have been observed, the spacing, Sobolev class, etc. And for the hypersphere, the most of them are related with the Sobolev class. All right, so a quick view on the Watson test, which is basically the Kramer-von Mises circular analog. So that is obtained by considering, rather than the second moment of Fm minus F, you consider the variance. Why so? Because then origin shift has no effect. So therefore, you achieve rotation invariance. You have a nice computational expression. Test is omnibus. Everything is known, asymptotic distribution. There is a local asymptotic optimality against certain alternatives, which is nice. So the whole picture is quite clear. But so far, only for the circle. Another interesting test is the Rothman test. So this one is based on evaluating how many points lie within an arc of length 2 pi t. So basically you think about an arc in the circle centered at value alpha, and then you count how many points are within that arc that spans plus t pi minus t pi. And then you scan through all the possible centers of alpha, and then you measure the quadratic deviation between the number of points and the expected number of points. That gives you the Rothman test. So this test is omnibus. If t is irrational, otherwise you can find alternatives for which the test won't detect them. And again, we know more or less everything about it. And if t is equal to 1/2, then this is related with the Agne test, and that's based on semi-arcs, and that can be quite simply extended to the hypersphere, because then it will be just looking into hemispheres. So we will see that later. All right, so then changing a little bit the ideas, a test for hyperspherical data that is relying on the projection paradigm is the one by Cuesta Albertos in 2009. And the idea is to characterize the distribution of the random vector throughout a random projection into the direction gamma, where gamma is chosen to be uniformly distributed. So therefore you have this characterization that holds with probability 1 between the null hypothesis and the projected null hypothesis. And therefore you can test for the uniformity by checking whether the projected variable follows what it should be the projected uniform distribution, which is this, I denoted by FP, but it's nothing but a beta distribution. And then, for example, you can do Kolmogorov-Smirnov for a particular gamma direction that was chosen randomly, and of course this has dependence on gamma, so a proper way of trying to alleviate this is by choosing several gammas, then tries to aggregate somehow all those results by, for example, taking the minimum of all those p-values, and that gives you another test statistic that can be calibrated by Monte Carlo, and well, there you don't know the asymptotic distribution or optimalities, but you can see that this is omnibus. So this idea was fundamental for thinking how to build up something else. And that something else will be presented next. So the idea is within the very same setting of Quest Alberto, so just take a direction, then project it, then test for the projected distribution. Then, okay, well, just do a simple tweak and then replace sup norm by quadratic norm, add a weight so that we can have some extra flexibility, and then let's study that statistic. So that's what we did, and well, that was the original definition of the statistic. Right, so then it still depends on gamma, so then the next point is, okay, let's try to alleviate that dependency on gamma. So obviously, let's try to integrate that with respect to the distribution of gamma. So this is indeed really related with Juan Carlos Scanciano ideas on the regression context, and mostly based or guided through the fact that at the end of the day, you can achieve a computable statistic. So this removes the dependency on gamma, of course. You have to deal with this guy, but we will see how to do that. And also an interesting point here is that the uniform distribution is the only distribution that you can put here, such that at the end of the day you guarantee that the statistic is rotation invariant. So the choice of gamma here is uniformly distributed is somehow canonical. Right, so this is the test statistic that we're going to study for different weights. So it has, well, if we expand it, we can see a pre-form of a U statistic. There is an integral there that we have to deal, and basically the main driver of the test statistic is going to be this term, which is going to be the proportion of the hypersphere that is, or the area that appears from the intersection of two hyperspherical caps that do not necessarily go through the origin, because there is this x there. So they will go through the origin if x is equal to 0. So you have to compute this thing. There are papers on how to compute that, and it's a little tricky because you can have up to 25 possible cases depending on the angles and so on. At the end of the day, it depends only on the smallest angle between the two observations. But if you sort of change the order of the intervals, and then you try to do first the one in the x, and then afterwards the one in the gamma, then you can work some expressions. So that's what we did. And for example, for the case in which W is a cumulative distribution function in 0, 1. So basically, we want to allow for having discrete weights in the statistic, not only continuous weights, but they will come handy later. Well, so we can work out explicitly, or more or less explicitly, what are the kernels for each W that you can have for this test statistic. So for the circle, then it's somehow neat, and then for higher dimensions, well, you start to need to deal with this FP, which is this beta distribution. But okay, it's a good starting point for afterwards coming out with kernel functions that are workable. An interesting point here is that without loss of generality, you can take the W to be symmetric with respect to 1/2. Well, that simplifies some of the computations, because if W is not symmetric, then you can symmetrize it, and the test statistic is exactly the same. All right, so now we have this expression. What's the game? The game is to take W's that are interesting. So, for example, we can take the one that will be associated to the Kramer von Mises weight. And then, okay, we can work out some analytic expressions. Just going to skip most of the details, but for p equal 2 and p equal 3, this is where the interesting stuff is going to happen. And if we analyze these two cases in detail, we have that for p equal 2, the test is completely equivalent to the Watson test that I described previously. And for p equal 3, it turns out that the test statistic is exactly the same as a test statistic proposed by Bakshaev for the hypersphere for dimension p equal 3, but only for dimension p equal 3. So we have two statistics that are defined for hypersphere, but they only intersect at one particular dimension in which they coincide. And so this is related with an energy-based distance test. Okay, and so recall that so how is this possible? Because there is an interesting point here, which is this test statistic. You take it for p equal 2, and this is not the Watson test, right? And that is somehow related with the fact that this new statistic has a dimension-dependent kernel, whereas the other ones have fixed kernels for each. The kernel is not dependent on the dimension. So this is the way why this test statistic can adapt its shape to different dimensions according to how the projected distribution is changing, and can give different test statistics as particular cases. All right, so we can play the same game for the Rodman test and then find the W such that somehow matches the Rodman test. If we work out the explicit form for the circular case, then we can match it with our projected class. We can do pretty much the same thing as before, having explicit expressions and so on, and then investigate them. I'm going to just to keep it short here for the finishing on time, hopefully. And so what we can see is that for circle, p equal 2, then we can see that this test statistic is completely equivalent to the Rodman test. And nevertheless, it's going to be working for any dimension. And in particular, if we take t equal to 1/2, what we have is that this test statistic gives, as a particular case, the test by Agne, which was defined for hemispheres. So it sort of makes sense that throughout this extension of the Rodman test from the circle to the hypersphere, we are maintaining the fact that the Agne test arises as a particular case for t equal to 1/2 in this extension to higher dimensional case. Just to say that these two tests were proposed from a different perspective. All right, and then if we keep playing this game and then we go with a non-integrable weight, and then we are a little bit careful, then we can have an Anderson-Darling type statistic, which now we have a closed form only for circle, but for higher dimensions, well, the kernel is specified. You can compute these integrals throughout Gaussian quadrature, and they are reasonably fast. And just to summarize what we have been doing so far, we have tested specific for S1 and S2. We have extended it to hypersphere, and then we have a newcomer, which is the Anderson-Darling here. Right, so how this relates with a class of tests that is really well known in statistics, well, in directional statistics, which is the Sobolev class. The definition is a little bit scary because it depends on eigenfunctions of the Laplacian. Well, there are quite some technicalities, but to keep it short, just let's say that it depends on the spherical harmonics. And so through that, you can build a basis in the space of square integral functions defined over the hypersphere, and then you have to project your data into those bases, and based on that, you can construct the test, which at the end of the day, the statistic of the Sobolev type has this form. So it's here in the kernel, this is an infinite sum of Gegenbauer polynomials that are related with the spherical harmonics, and such that we have some coefficients over there. So indeed, this looks really similar to what we have been doing. Indeed, if we take a kernel of our class and then we project into the family of Gegenbauers, then we somehow have that the kernels kind of match. Okay, so we have some coefficients there and some coefficients there that are similar. So the question was, are the two classes completely equivalent? What are the differences? So that's what we investigated. So matching these two coefficients is not so simple because the ones for the Sobolev test are positive, whereas the ours do not necessarily need to be so. Actually, answering that question amounts to answer whether the kernel is positive definite on the hypersphere, and that's a slightly tricky thing to do. And also, provided that we are able to do that much of the kernels, what will be the way that will give me one kernel? So that will be related with an inverse problem in which W will be the unknown of this integral equation. So just to sort out this relationship between these two families, we can define this notation. So let's call SL to the Sobolev tests that are truncated at L, so that the coefficients are 0 from L onwards. So of course, as infinity will be the full Sobolev class. And then we will have our statistics indexed either by probabilities in 0, 1, or also we went as far as considering signed finite measures on 0, 1, because we needed that in order to be able to solve this integral equation. So what are the contentions? Well, basically, if we are talking about what could be a sensible projected test in the sense that it will be indexed by a probability, then essentially our tests are part of the Sobolev family. Yes, we get new insights and new tests and so on, but at the end of the day, we are contained in the Sobolev test for this family of sensible tests, let's say. And then on the other way around, if we have a finite Sobolev test that it projects exactly into up to certain eigenspace, then we can map them back to our framework if we allow W to perhaps be signed. So let's say, in other words, we cannot guarantee that this won't be signed. And we have counterexamples showing that all those inclusions are strict in a sense. All right, so on one sense, this is bad because, well, they're part of the Sobolev class for the sensible things. On the good side, then we can borrow all the asymptotic theory from that. That's where the work gets easy. And basically, we have the null distribution as results for the Sobolev class, and then we have consistency. We are able to prove that all the coefficients are positive, and we have some optimality against specific alternatives. So how much time do I have left? I'm not sure.
About
10 minutes. My good. 6 minutes. Okay. So we have some locally and asymptotically optimality against this family of alternatives, which is just, well, basically a mixture of the uniform density on the sphere with some alternative that is also indexed by these coefficients B's. So basically the coefficients B's in which I project my kernel are the ones that are going to drive afterwards what is the asymptotic distribution, what is the local optimality, and eventually what is the omnibusness if I'm able to prove that all the BKs are positive. So these are results borrowed directly from Ginet in 1975. Okay, and then we can work out specific coefficients and provide the specific answers for the Anderson-Darling test and for the Kramer-von Mises test for some dimensions, at least for the most important ones, although, well, we will be working on extending this for high dimensions. And just to say something about the simulations, right, so what we did was to compare several tests for different, for the local alternatives and for different, for other alternatives for which we don't have optimality within this class, but we have tests that are optimal against those alternatives, such as the Rayleigh test or the Bingham test, and then see how we do and whether we won with the proposal by Cuesta-Albertos. So these are the results in S1 in the circle. So here in orange we see the new proposals, and in blue we have the one by Cuesta-Albertos, which was kind of the main driver for the work. What we see is with the Anderson-Darling test, where is it? Okay, over there. So we won, let's say, for 3% to 8%, more or less. So the winning is not massive, I must say. The test was performing better than we anticipated. I mean, Cuesta-Albertos stuff. But still, we gain some power. And on top of that, well, it's the fact that these tests are not random, because this whole simulations are, for the Quest Albertos, are conditionally on the fact that you have chosen 50 directions randomly, and then you have all the Monte Carlo studies conditioned on that selection, because otherwise the calibration is not really feasible. So that means that the result will change if I say I run the simulations with other 50 directions as the projections. All right, and then of course we have some optimality for the deviations for which the Kramer-von Mises should be the optimal, for the ones for which the Anderson-Darling should be the optimal, Rothman, von Mises feature here it should win Rayleigh, and also for the Bingham. For the angular central Gaussian should win Bingham. So there are a lot of results, but also some interesting thing is that when we go to higher dimensions, the Anderson-Darling seems to be even winning in the alternatives for which originally the Kramer-von Mises and the Rothman should be winning. I'm not so sure whether that's an artifact of the sampling device, because it's based on the truncation of a series of Gegenbauer polynomials, but even with that, it's surprising the fact that with just a little inaccuracy, perhaps, in the sampling device, then the Kramer-von Mises and the Rothman test lose their optimality, and that is picked up by the Anderson-Darling test, which, all in all, was performing quite satisfactorily, I must say. So in S3, that becomes even more relevant. Also for situations in which we have, for example, a unimodal alternative, such as the von Mises, here the Rayleigh should be the optimal one. Well, here we see that it's not performing so far away from the optimal one. All right, so I just conclude with the main points. There is a projection integration family of uniformity tests. There are extensions of specific tests for specific dimensions. And thanks to this new family, we have an Anderson-Darling test. And there is a connection with the Sobolev class that we have studied, and there are several empirical power improvements. So thanks for your attention.
Any questions?
So when we came here, we talked about tests.
Yes.
Other tests. I can even add another test.
No.
In any dimension.
Okay.
For each point on the sphere, look at the nearest neighbor with respect to the quadrametric.
Yes.
Then you have a volume, how's the volume of the spherical cap to this next neighbor. From these take the maximum of the volumes. This will give you a consistent test for uniformity.
Okay.
The limit distribution under the null hypothesis is the Gumbel distribution. You can even prove a convergence limit theorem for the number of exceedances of those spherical caps that only contain one point in the middle, which is the point from which the nearest neighbor is measured.
That's great. Thanks for the suggestion. Is the paper published, or is just an idea of a potential?
But I never pursued this idea further.
Okay.
I alluded to, but you can really work it out.
That's great. So it is really related with the vacancy test in the circle. You have a pretty...
to the largest spherical cap.
Yeah,
It
yeah.
doesn't contain any point, which gives you also a consistent test. But here, of course, the nearest neighbor implies it must be one point in the middle.
Yes.
So you look for the largest, let's say, cap, starting with the nearest neighbors.
Yes.
The largest nearest neighbor cap.
Yes. So I just wanted to add that there is indeed this maximal gap test in the circle. It has pretty much this analog distribution. It's a gamble, certain parameters. I don't remember exactly. I think it was by Cressy in 1977. I'm not so sure. In the circle only. Thanks. Thanks for the suggestion.
So these projections became very, very popular in the 1970s when people discovered or rediscovered a paper written by Radon in 1917. And they found out that is useful for very special applied things. And that was the basis of the computer tomograph. So the work of Radon, which was based on what is now called the Radon transform, is based on also performed. So there was an increasing interest also in the numerical analysis, not only the statistics, and they connected the radon theory to the Fourier analysis.
Mm-hmm.
So maybe also, I have not seen this in your talk. What these people found out, for example, what I saw in your talk, the Gegenbauer.
Yes.
Gegenbauer
Yes.
functions. So they use what you said, also this spherical harmonics.
Yes.
Yeah, but their data are not random, but there is some numerical work, so there is some interesting connection.
Mm-hmm. So if you go to dimension 2 in the circle, then, those Gegenbauer polynomials transform into the Chebyshev polynomials, and then you have the Fourier analysis, and then the Sobolev tests are pretty much Fourier decomposition, and you have the connection over there.
We have time for one more question. Okay, next time to speaker. Next speaker is Zuzu. You may continue.
Yep. Okay, so it's my pleasure to come to this workshop. So I would like first to thank the organizers to inviting me for inviting me here. So what I will talk about today is a little bit different from the first two topics, which is about Goodness fit. So my topic is about change point analysis. So particularly, what I'm trying to discuss with you is a change point situation where you are trying to detect change points in a something what we call a complex temporal dynamics, where you have a very non-stationary environment where things are actually constantly evolving over time. So in this kind of thing, in this kind of situations, how can we do a change point analysis? Is something I want to discuss. Okay, so first of all, this work is jointly with my former PhD student Wei-Chi Wu. He's now in Tsinghua University in China as an assistant professor. Okay, so before we start, we can take a look at a very illustrating example. So it's a toy example, actually. So it's actually an example of, you can see from the caption that it's actually a square and difference hourly North Atlantic wave heights recorded at a buoy is something actually a floating device. So basically a buoy is a floating device. And the number of the buoys there. So basically, it's actually a location very near Nova Scotia in Canada. So basically, it's so you can see that. So basically, the first graph actually shows the data. So it's squared and differenced. So a very important thing actually people want to detect in this time series is basically it's the variability of dynamics of the variability of wave heights. So you can see that when I square things, then become the mean of the squares is actually the trend of the squares is actually the volatility or the variability of the original time series actually. Okay, so you can see that actually here the second and third and fourth graphs are actually the fitted mean variance and the lag one autocovariance using the method I will propose in this paper or in this talk. So you can see that actually the time series is quite non-stationary. So basically, let's just first take a look at the variance and the lag one autocurrence. You can see that there are at least 6 or 7 abrupt change points where we detect. So those vertical lines are the locations of detect change points. But besides those abrupt changes, it seems that the the variance and the autocovariance also smoothly changes in between the abrupt change points. So in other words, you can see both smooth changes and also abrupt changes in the system, in this system. Okay, so this actually example illustrates the problem that I'm going to tackle, all the actually data structure I'm going to tackle. So that the data structure is a complex data structure where your underlying data generating mechanism is actually both smoothly changing and also abruptly changing sometimes. Okay, so that's basically what I'm going to think about. All right, so by the way, so this data set actually was considered in the 2012 paper. Actually, if you are familiar with maybe change point detection techniques, there's a paper called it's called PELT, so P-E-L-T. That paper by a group of British statisticians published in JASA in 2012. So this data set was, I think that was the first time that this data set was used. And this data set also is available from our package, so it's very easy for you to get it. Another challenge in this data set is this data set is pretty long, actually. The length of the time series is more than 63,000. So to analyze change point in this kind of data set, a very important problem also is how to actually do efficient computation. So in order to get things right in a short time. Okay, so let's actually, first of all, do some kind of a high-level thinking of this kind of problem. So because the very important thing, actually, or a very sort of like dominant thing in the current literature of change point analysis is that people usually want to actually make the assumption that the parameter of interest is actually piecewise constant function of time. So it's very, very dominating in the literature of change point analysis. So that kind of assumption is I would say, it's very technically convenient because if you have piecewise constant parameter of time, then it's actually something related to segmentation. So you just segment the series into stable or constant periods. So that's convenient, but on the high level of logically, I think that's also a little bit debatable that whether it's actually quite suitable for many practical situations. The reason is because we can think in our mind, it's very easy for you to think about a system of time, a temporal system, which actually evolves smoothly over time instead of piecewise constant. Smooth changes and actually slowly changes are pretty much a very common thing in real practices. So therefore, actually, what I'm thinking about is that I'm thinking about maybe it's better for us to think about, especially for complex temporal systems, it's better for us to think about piecewise smooth models instead of piecewise constant models. So that's something I'm thinking about. So there are a few benefits of the piecewise smooth thinking. So I'll just list a few of them. The first of all is that definitely piecewise smooth function is a piecewise constant function. So piecewise smooth class is actually much bigger than piecewise constant class. So it's actually a bigger class. Another view is that, so basically, it's very important for us to distinguish smooth changes and abrupt changes because those two kinds of changes will have different physical meaning and different interpretations and different consequences. So those two kind of changes are very different. So it's not very good for us to actually only think about one of them. Okay, so that's another thing. The third thing is that actually, if a time series data generating mechanism is really smoothly changing, then if you force it to actually fit a piecewise constant model, then actually it's actually not so. So that's the fourth point. Actually, it will give you a lot of spurious change points. So in other words, if you fit a smooth system by piecewise constant curves, definitely you will get a lot of change points, which are actually pretty spurious, I would say. So therefore, actually, there are a bunch of things that we can think about in terms of which model is more appropriate in real applications. Okay, so that's actually something I want to talk about in the high level of thinking of these kind of things. And so, but there are actually many challenges once you want to actually abandon the piecewise constant logic thinking and you want to adopt a more complicated model to your change point analysis. There are a few challenges. The first challenge is that, so since you have a very non-stationary system, and then it's not, usually the single scale methods are not very, very good for those kind of complex systems because the scales that you want to, so at different time points, the scales which are appropriate for detecting change points will be different. Actually, those scales will constantly changing over time. So therefore, it's very hard for us to pick a single scale which is actually universally applicable for the whole time series. Therefore, it's better for us to think about multi-scale methods in this particular situation. So multi-scale methods, I think, is more appropriate for change point detection under complex temporal dynamics. And the second thing is that sometimes in this complex temporal dynamics, sometimes it's very difficult for us to distinguish about abrupt changes in the mean and abrupt changes in the higher order. So basically, I think most of the state-of-the-art change point detection method assumes that the covariance structure of your time series is actually stationary. So definitely it's not all of those, but many of them, the state-of-the-art change point detection method assumes so. So therefore, from our simulation studies, we found that a lot of change point detection methods will detect the wrong number of change points once you add non-stationarity in your covariance. Okay, so that's basically a lot of times that's happening. So in other words, it's a very important task for us to think about how to distinguish change points in the mean and change point in the higher order structure of the time series. And the third thing is that, as I said, the time series nowadays is getting actually longer and longer. So you can get, like, for instance, even 100,000 or even longer time series. But a lot of times, for especially change point detection algorithms, it's very important for us to think about how to make things more efficient. For instance, especially in the case where you want to do online detection, then definitely a very, very important thing is computation efficiency. And the fourth thing is that, so once you have this kind of very complex temporal dynamics, then it's not so easy for us to establish a theory about the behavior of your change point detection methods. Okay, so those are a few actual difficulties we have about this kind of problem in particular. So what I will do next is sort of like I will give you a non-technical review of some methods I have recently developed with my student and see actually and some results about those. And so the first thing I would like to discuss with you is actually what do I mean by complex temporal dynamics? How do I actually have a rigorous mathematical model or statistical model to describe the non-stationary dynamics that's both smoothly and abruptly changing over time? So that's very important. Otherwise, there's no way for us to establish a theory. So therefore, it's very important for us to think about a model. So that's why in this slide, I will introduce you what we call a piecewise locally stationed time series model. So I think a lot of you have heard about locally stationed time series models. So that's actually a model which was first proposed in the 1960s and then was sort of renounced in the 1990s by Rainer Dahlhaus, and then actually there's quite a lot of work there. So basically, locally stationed time series assumes that the time series data generating mechanism is smoothly changing over time. So what I have added here is a piecewise adjective there. So piecewise local stationary means that the time series is locally stationary in segments of the data. So in other words, your data can be segmented into many locally stationary segments. And at those boundary points of the segments, the data generating mechanism is actually abruptly changing over time. However, in between abrupt change points, the data generating mechanism is smoothly changing over time. So that's basically what I mean by piecewise local stationarity. So I don't want to bother with you about the formal definition because I don't think I have time. It's only 30 minutes. So, however, basically what I mean here is that so you have like abrupt change points CJs. So on those CJs, the data generating mechanism of your time series can jump from one to another abruptly. However, in between CI and CI plus 1, the data generating mechanism is actually smoothly changing over time. So that's what we mean by piecewise local stationarity. Okay, so you can see that this framework actually allows both abrupt and smooth changes. So I think it's a relatively flexible model for complex temporal dynamics. Okay, so the time series model, I'm thinking the problem I'm tackling is this. So YIN is your observed time series. For instance, it will be the wave height, Atlantic wave height time series you observe. And it's actually can be written in a function fn-ion. So fn is actually a piecewise smooth function of time. And epsilon-in, the noise epsilon-in is actually a piecewise locally stationed time series. And I assume that there are actually mn change points in this f function. So the change points are d1, d2 up until dmn. And this mn can diverge. So in other words, the number of change points is allowed to go to infinity as the time series length goes to infinity. Okay, so that's basically the framework I'm thinking of. All right, so what the most important ingredient of this change point detection technique is something I call a jump path filter. So what is jump path filter? Actually, jump path filter is actually a wavelet function. And this wavelet function is supported on -1 to 1, and it's actually an anti-symmetric function. And the integration of the wavelet function w with respect to x to the power u is 0 for u from 1 to k. So if you're familiar with wavelet theory, this basically means that the wavelet here is of order k. And there's another point which is very important about this wavelet is that this wavelet has to satisfy this condition. And this condition looks very complicated, but this condition basically means that if you apply this wavelet to your time series, and you apply this wavelet to the time series, then the peaks of those applications will be exactly at the jump points. Okay, so basically this actually means this assumption actually makes the peaks of the application of W to actually localized at those jump points, which gives us accuracy in terms of estimating the jump points. Okay, so that's quite important. So in the common sort of wavelet theory, there's no restrictions about wavelet function having this, but because we are dealing with a sort of like a change point problem in specific. So therefore, we actually has to have this in order to make the change point detection algorithm accurate. And also, we do not assume that this W actually is sort of like orthonormal basis. So there's no need for us to assume that W is orthonormal. Okay, so it turns out that the change point detection sensitivity is very, very important. It's very, very related to this quantity, which we call it the singular noise ratio of W. So we actually want to maximize this S and W. So it turns out that you can do that, but it's actually complicated, but you can do that. And it turns out that you can actually get an optimal filter like this. So basically, this is an optimal filter in W26. So W26 means that the wavelet order is 2, and we are searching the optimal filter in polynomials of degrees of 6 or less. Okay, so that's basically the optimal filter in this class. So why we don't choose W to infinity, it's actually another story, but it's long to tell. But anyways, to choose W to infinity is not good. So basically, once your polynomial's degree gets gets higher and higher, the optimal filter will become more and more rough. And then those things will not become very good for change point detection. So, all right. So actually, now I can introduce you what is the multi-scale change point detection statistic. So the multi-scale change point detection statistic is the supreme over all the scales from the lower bound of the scale to the upper bound of the scale of this function G. So what is G? G is basically a studentized, or sometimes people call it self-normalized version of the application of H to the original time series, as you can see. So H basically here, this H function is the application of the W of the wavelet to your time series at time t and at scale s. So you can basically see that. So then actually you just think about this H and then do a studentalization of this H. And so, but you have to take this over all possible scales from the lower bound to the upper bound. In other words, you want to actually get the maximum evidence against the time series, against the hypothesis that the T is actually a jump point or a smooth point of the function f. Okay, so this is very, very important. The supreme here is very important. Otherwise, if there's no supreme, then it becomes a single scale test. But single scale test usually does not perform well in complex temporal dynamics. So that's why you have to have this multi-scale type of thing. So now, actually, this slide is just for technical reason. I have to introduce certain kind of quantities because the next slide, what I want to do is I will introduce you what's the limited distribution of the multi-scale statistic. So basically, that I need to do this preparation. As you can see, that all these quantities depends on the lower bound of the scale and the upper bound of scale in a complicated way. So if you have those preparations, you'll find out that the maximum deviation of the main statistic, which is the key in terms of doing this statistical test or the estimation, is in this form. So basically, the maximum deviation of your multi-scale change point detection statistic is the limited distribution is like this. Okay, so if you have a limited distribution like this, you can see that this limited distribution depends on many things. The most important thing is that this limited distribution depends on the lower bound of the scale and the upper bound of the scale. So it's very important. Definitely, the distribution also depends on your W, your filter, or your wavelet function. It turns out that actually this is very helpful in terms of helping us to actually evaluate to actually do the fast change point detection. The reason is because if you don't have this limited distribution, then a lot of times people have to do bootstrap in order to get the distribution of to do change point detection. However, if you have a time series of length more than 60,000, from our experience, if you want to do a bootstrap or something or some other resampling method in the ordinary way, it usually takes more than 10 or 12 hours for you to finish the bootstrap. So you can try yourself, but it's actually pretty time-consuming if you want to do bootstrap. However, if you have this limited distribution, then you will be able to do it very fast. But the multi-scale limited distribution is a very difficult problem. So basically, I'm very happy that actually we can derive this. So this actually can save us a lot of time in terms of doing the inference. Okay, so the next thing is about the algorithm. So the algorithm is not so difficult. So the algorithm basically actually is just a sort of an iterative or way to find all the change points. So you first calculate the G function there, and you calculate the critical value of your limited distribution based on the closed formula. And now you can actually find out the peak, the first highest peak of your G function. And if that peak is above your critical value, then that's a change point. And then you remove that peak and then try to find another peak, the second highest peak. If the second highest peak is still above the critical value, then that's another change point. And you just do that repeatedly, you will be able to find all the change points. Okay, so that's a very, very simple algorithm to think about. Okay, but how is the performance of the actual change point detection algorithm is very important. So definitely, we all know how to do it, but it's just what's the performance of it. So it's a very important thing. So it turns out that we can establish the following thing is that, so if there's no change point in your data, then the probability that you will detect zero number of change points will go to 1 minus alpha. So basically, alpha is the number you choose. For instance, you can choose it as 1% or 5%. It's up to you. So if there are mn change points, then the probability that you detect exactly the correct number of change points, and each change point is within hn of the true change point will go to alpha, 1 minus alpha. Okay, so that's basically the result. So what is HN? HN is this thing actually looks very messy. And actually, we don't like this HN because this HN is not optimal. So the next thing I will tell you is that how to actually make this algorithm more accurate. So the second thing I will do is something called a second stage refinement algorithm. So basically, we want to make the change point detection, the change point location better, that estimate change point location. So the second stage refinement is based on something called a local Q-sum test. So basically, I will first have a rough estimate of the change points. And then now what I will do next is that I will actually try to do around the estimated change points a local Q-sum test. And then I will find the maximum of the local Q-sum tests. Okay? So it turns out that if you do the second stage refinement, that the probability of estimating m hat equal to m, so the number of change points is accurate, and each change point is within this range of the true change point will go to 1 minus alpha. And it turns out that those rates So this m to the power 1 over p minus 1 log n divided by n, and this log n to the power 3 divided by n, those are optimal. So in other words, they are optimal parametric rates. So if you have parametric change point detection algorithms for IID data, you can only get this kind of rates. Okay, so you cannot improve it. So in terms of this sense. So in other words, if you do second stage change point refinement, the maze actually can detect things within an optimal range. Okay, so this is about another situation. This rate here is also optimal. So in other words, this second stage of refinement is quite efficient in terms of making the change point detection accurate. Okay, so now let me try to talk about the computation efficiency of change point of maze. So as you can see that, so the actual asymptotics of maze is actually for all the, you can see that it's actually for all the scales from the lower bound to the upper bound of the scales. However, in practice, we cannot calculate so many scales because it's so time-consuming to calculate the statistics for so many scales. Actually, there are infinitely many scales. So the remedy we have in terms of computation is to actually take a small number of scales. So we'll take this many of scales. We'll only take log n to the power 1 plus epsilon scales from the lowest from lower bound of scales to the upper bound of scales. And it turns out that if you calculate the maze statistics on only log n to the power 1 plus epsilon scales, the limited distribution of your sparse version of maze and the dense version of the maze is asymptotically equivalent. In other words, there's no loss for you to calculate the maze statistic on a sparse grid of scales. So the limited distribution is the same as the dense case. But computationally, this is much, much better because you only calculate log n to the power 1 plus epsilon scales. And at each scale, actually, to calculate the maze statistic, the computation cost is O n. N is your time series length. Therefore, in combination of these two, actually the computation complexity of this maze statistics is just O n to the n times log 1 plus epsilon n. Okay, so it's quite fast, actually. At least theoretically, it's quite fast. Okay, so actually, you'll find out that actually there's another benefit of using maze. The reason is because for different scales, for instance, if I calculate different scales, one is S1, one is S2, the calculation of these two different scales is totally independent of each other. So therefore, you can do parallel computing of those. So because they are not related to each other. Think about other actually algorithms. For instance, if you are familiar with PELT or wild binary segmentation, those kind of things, it's hard to make them parallel computing. It's hard to actually do parallel computing of those algorithms. Okay, so therefore, actually, maze is actually quite good for computation efficiency if you know how. Actually, in our paper, unfortunately, we don't know how to do parallel computing. We didn't do it. But theoretically, you can actually do parallel computing for maze. It should be not so difficult, I think. If you have a very good cluster with thousands of CPUs, the maze can be actually done very fast in those clusters. Okay, so let's take a look at those simulations. Okay, so I still have time. So let's take a look at simulations. So I have two means. So the first mean is piecewise constant mean. So this is actually this mean number one is actually the assumption made by many of the past algorithms. So in past algorithms, people usually assume actually the function is piecewise constant. And the second mean is piecewise smooth. In other words, it's in our domain, but not in the traditional domain. Okay, so there are a bunch of errors I'm thinking. So basically, there are IID errors, there are piecewise stationary errors, there are ARMA errors. So ARMA is just it's a stationary linear model. There is a locally stationary error, LS. There's a PLS error. So PLS is piecewise locally stationary model errors. So it's thinking about many different kind of errors. So this is actually the simulation results. So we compare maze with 3 different methods. Definitely, there are more of them, but because we are thinking about multi-scale change point detection, so therefore we compare our method with 3, I would say, very popular multi-scale change point detection methods. So this H-smooth is a paper, I think it's a GISP discussion paper in 2014, probably. So it's actually a sort of like it's a penalization-based method. So penalize the number of change. So you penalize the. I think you maximize the number of change points by penalizing the goodness of fit. Okay, so that's basically what H-smooth does. And H-smooth allows a little bit heteroscedasticity in the error, actually. The WBS is something called binary segmentation, so wild binary segmentation, actually. So it's actually, I think it's also I forgot, but anyways, it's a British group, and it's a multi-scale measure too. So PELT is based on dynamic programming, and there's a pooling stage to make the calculation very fast. So basically, there are 3 algorithms we are comparing. And you can see that actually for stationary, so this is IID error, GS is for IID error. So for IID error, you can see that H-smooth is not performing very well, but WBS and PELT is performing okay. And MACE is performing okay too. And you can see that actually the MAD actually talks about the accuracy of the estimation. You can see that for IID errors, the accuracy of MACE is very similar to WBS and PELT and also H-smooth. So in other words, the accuracy is quite okay. And for ARMA models, MACE is okay. However, H-smooth starts to actually crash. So basically, it doesn't work for dependence because H-smooth is not designed for dependent errors. It's only for independent errors. And WPS also crashes because it's only for independent data. But PELT still is okay. So PELT is still okay. But so once you go to more complex temporal dynamics, for instance, once you have piecewise stationary models or locally stationary or piecewise locally stationary models, you can see that none of the H-smooth, WPS, and PELT will work because they are not working under the case where you have non-stationarity in your covariance in your error. Okay, so the next thing is about actually the piecewise smooth errors. Sorry, piecewise smooth signal. So once your mean is piecewise smooth, then none of those things works. It's 0 detection because they assume that the thing is piecewise constant. Okay, so if you have piecewise smooth, it doesn't work. Okay, so and I will not bother you with all those. I think it's better for me to conclude the talk. So let's go back to the wave height data. So for the wave height data, you can see that this is basically that we have detected 3 change points in the wave heights. And in between the change points, you can see that the wave height actually, interestingly, is annually periodic behavior. So in other words, the wave heights, the variability is actually annually periodically behaving like this. However, if you use PELT and WBS to detect change points, the fitted mean function will be like this because they make piecewise constant assumptions. So for those kind of piecewise constant fitted curves, you probably cannot observe those periodic behavior of variability of wave heights. Okay, so what I think is that so they detect more than necessary change points because of the smooth changes of wave variability. So that's our opinion. Definitely, you can debate about this. But anyways, so and also the final note I want to make is that so basically the H-smooth. So H-smooth, the result is not listed here because the time series is more than 60,000 lengths. So H-smooth doesn't give us results because the software they provide cannot deal with the time series this length. The length is so long for them. Okay, so that's pretty much I want to talk about today. So thank you.
Is it on? Yep.
Yes.
It seems to me that your paper is very interesting. It seems to be a generalization of a paper by Beran and Shumeiko, 2012, in the Journal of Multivariate Analysis.
Yeah, so it's very good for you to mention to me this because I'm not aware of that paper. But yeah, I know that there's actually 1990s paper about detect changes in the piecewise smooth signal by like Hans Müller, and there are
that paper looks at a time series with trend functions and long-range dependent.
Oh, long-range? Yeah, this is not about the long-range dependent. This is short-range dependent, but it's non-stationary.
Yes. No, I mean, as far as data is concerned, locally stationary processes where the regime may change sometimes may look like long-range dependent.
It's good that after the talk I can come to you to ask for the paper. Maybe you can give me a reference and take a look at it. Yes.
Practically speaking, it may actually work also quite well for such data.
Okay.
There, wavelet decomposition is used, and a test for continuity against discontinuity of the trend function is based on father and mother wavelets. Mother wavelets contribution is the one that takes care of discontinuities.
So, was that paper multi-scale or single-scale?
Multi-scale. It's a
wavelet
decomposition. It's exactly what you are doing.
Yes,
it's exactly what you are doing, just that you are testing for change point. And
I see.
One test just for continuity or discontinuity of the trend function, which is actually the same thing.
Okay, great.
And you have, we have a piecewise continuous trend function, possibly under the alternative, and you are testing for that.
Okay.
So that's
it's great. Yeah, it's great to know that. Yes.
Any more questions?
Just two small things. One thing is you were saying at certain moment that you would use for certain problem the local COSUM. So that maybe there is something related to MOSUM. There are moving sums. So there is a paper about it.
Okay.
So this is one thing. The other thing is that you were speaking how you are choosing the estimators of the possible changes.
Yes.
But that what you were mentioning, how I understood it, something close to the method proposed by Vostrikova in 81.
Okay, yes, definitely. That's very commonly used method.
But you see, one must be careful because it doesn't detect all possible changes, and that can be in your case also.
Okay,
but I don't tell you more.
Okay. Yes.
Hello. So I wanted one clarification. So you take the supremum over all scales.
Yes.
So if you want to get abrupt change detection, why don't you focus on the supremum over those smallest scale that may reflect the abrupt change?
Yes. So so that's a very good question. So the allowed change point range is actually small ranges. So basically, we will first restrict ourselves to small scales, and among those the small scales, we choose a lower bound and upper bound, and then we choose the maximum over that. So we cannot choose the scale which is very large because that will mess up with the smooth trend, and then things will be messed up. So basically, first of all, the scales need to be the allowable range of the scales is actually first of all will be actually small. Those small ones. Yes.
Hi, great talk.
Yeah, thank you.
There is a paper also with Jan Veron actually, where we look at points where the first derivative is above a threshold. Okay. So, did you any comparison? This actually
that's a good question. So yes, we haven't done the derivative part. So but I think the method can be modified or can be extended to the case where you want to detect changes in the derivative of your function. But this one is not designed in that case. Yeah.
Okay, so this is not changes in the derivative. This is changes in the trend function.
Yes.
Yeah, but you simply check where the change is very fast, where the trend is changing very fast.
Yes.
Therefore, you look at the first derivative.
Then, yes. When the trend is changing very fast, then it's better for you to think about it as a break. Yes, that's right. Yes. Right.
Okay, so I think we are over the time, so we'll have a coffee break.